So stuff gets bigger when it gets hotter. And that idea is called thermal expansion. I want to understand it a little bit today. Thermal expansion works like this. You take some stick of metal or something, and let's say that it starts out this long. It's a solid stick of metal, and I'm saying that it's that long, and I want to heat it up, and so I do, and I'm gonna say that the change in length, that's this right here, dot, 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 that change in length depends on some stuff. Change in length is going to depend on the change in temperature. That's the first thing that I learned. If I change the temperature by a little bit, the length changes a little bit, and if I change the temperature by a lot, the length changes by a lot. So it depends on some constant too, though. And I don't know yet what that constant might be. But I want to ask you a question. What if I took a chunk of wood that was maybe twice as long as this? What if I had a chunk of wood that was 2 L0 long, and I asked you what I could expect its delta L to be as I increased its temperature by the same amount? So delta L equals question mark. What do you think? Do you want to take a guess at that? Well, one way of looking at this is that this chunk of metal is 2 chunks of metal. There's one here that's L0 and the other one here that's, let's see, draw this L0 a little more carefully. Here's an L0 and here's another L0. And there's 2 of them here and just one of them here, so this one's going to expand by this delta L, this one will expand by that delta L. So I guess I'm implying, right now I'm implying that this constant has something to do with how long it starts out. This is a little counterintuitive, so make sure that you believe this equation I'm about to write. I'm going to say that the length change of a thing, which really, I mean, strictly speaking, length change is L final minus L0, but L final minus L0 depends on L0. Wow, this is going to be a little bit interesting. So I'm saying that the change in length is L0 times delta T, but we still have to have some constant, right? Because we don't even have the right units here. This is supposed to be length, this is original length, this is temperature, so that's going to be in Kelvin, and this must be in some weird units of like inverse Kelvin, this other thing. I'm going to just call it a constant, and I'll call it alpha. Let's get some pink going on here. I'll call it alpha, and alpha is called the coefficient of linear expansion, and I'm going to say that it, well, I mean, we could just define alpha to be delta L over L0 times delta T, sure, and look at the units of it. Delta L and L have the same units, so alpha's units are 1 over Kelvin. And I guess that's the same thing as 1 over a Celsius degree. Interesting. Interesting. I guess that's really cool. This alpha probably depends on the material in question. So 2 different metals might have different expansion coefficients. And I want to ask you a question. What if I had a metal here? What if I had one strip of metal and I noticed that it had a small alpha and another strip of metal and I glued it to it, and my other strip of metal has a large alpha, and I heat it up. It's getting hot in her. And my question is, would this, when I heat it up, would it look like, whoa, that's kind of slappy. Would it look like that? Or would it look like this? That's my question for you. You got to figure out what's happening, whether this guy will be, that's frustrating. Sorry. Whether we will be having it bend downward or bend upward. And this makes us extremely powerful, because now we can set this up and actually measure the temperature, because this bending will be twice. I guess there's something that I should tell you. I want to clamp it here let's say that I clamp this right here, so that it's twisting about this little clamp location. That's one thing that I have to make clear. We can make a really cool device that can indicate the temperature based on the twisting of this metal. And the longer we make it, the more twisting we'll get. We'll be able to amplify our twisting by making it really long. If we make it really long, it might actually twist up on its own, and we'd have this. Let me show you without that reflector to see what's going on here. We've got what looks like a spring, but it's actually called a bimetallic strip. And the reason is that it has two metals in it. And the bimetallic strip is used in all sorts of devices to indicate the temperature or test the temperature. So we can set this guy right here on this thermostat, and boop, it tells us what the actual temperature is. So somebody in a house might want to know what the temperature of their house is, and you just put a little bimetallic strip in there. This thing costs pennies to make, and you can indicate the temperature. And if it gets hotter, then that temperature will go up. Let me see if I can do that for you. It is presently reading 70. So, in the spring. But, suffice it to say that this could work if you knew what you were doing. And I don't. But, you could also set a bit of mercury in a glass tube. And see in there, I've got a bimetallic strip in there. See that sucker right there? The same kind of thing, but it's a much tougher bimetallic strip. And if the temperature goes up, let's say this is on a furnace. If the temperature goes up, it will make the mercury go to this side, which doesn't cause contact between the two terminals inside the mercury, inside the tube. And if the temperature goes down, then this will twist like this. Oh, and it says, hey, it's cold. Turn on the furnace. And now this sucker right here, this inert little pile of metal that sloshes from side to side, will regulate your temperature for you. Awesome. Pre-computers on, off, based only on the properties of these two metals. One expands differently than the other, and you have a comfortable house. Nice work. You could also set up some other contacts in there. This is a more complicated thermostat, because it's also able to turn on cold and turn off cold. I guess the contacts are on the opposite side. Not any big surprise right there. The next thing that we need to discuss is area. What if instead of just a linear expansion, where we've got this delta L right here, instead of delta L, what if we were talking about some area expanding? Area expansion is interesting. So I would say that if I start with some area, let's call it A0, then I'm going to have some expansion, and the cool thing is that expansion will be like this and like that. I'm going to pretend that I bolted down this side and I only let it expand that direction. So I'm going to say that area prime, that's my new area. Area prime is, well, each dimension, this dimension and that dimension. Here we've got L0 and L0, and here we've got delta L, and here we've got delta L. Each dimension is expanding by the equation L plus delta L. That's the new length, and an expansion is the delta L right there, and I need to square it, and this is equal to, well, let's go crazy with this. This is L plus alpha times L times delta T, sucker, square, just the same as it was before. We're just using the definition of delta L that we derived previously, but it depends on L0. You want me to put some L0s on here? Yeah, let's do it. L0, L0, L0. There we go. Now we're honest and true about it. And now I'm going to expand this little, let's expand this sucker. I'm going to say that that is, well, it's L0 square, and then I have to add 2 times alpha times L0 times delta T. And what am I going to have? That stuff there? Yeah, I guess so. And then I'm going to have alpha square. Wait a second, we need an L0 in here, don't we? We need an L0 square right here. Yeah, because we got L0 times that sucker right there. And this is alpha squared times L0 squared times delta T, that quantity squared. And the awesome thing about alpha is that alpha is small. So look at this term right here. This term has alpha square in it. alpha is much, much less than 1. And we can neglect this term. Standard physics technique says we don't want this one. And I'm going to spell neglect correctly even. Look at you. Bonus, right? So this is now our area expansion neglecting this tiny little bit right here. That's pretty small, right? I think it is. Excuse me. So we'll go back to purple for the close. And the close says, guess what? Area prime, our new area, is our old area, plus 2 times alpha times L naught square, oh, that's area, times area times delta T. Beautiful. But of course you knew we weren't just talking about area. You knew that we were interested in investigating volume. But let's see, if I were to simplify this, I'd say change in area, that's going to be area prime minus area naught, is, excuse me, 2 alpha area naught times delta T. And this is the equation that's analogous to our length equation, but there's a 2 in it. Let me remind you that change in length is alpha L naught times delta T. Wow, that should be capitalized. Make sure you capitalize that. Finally, volume. Volume is where it gets interesting. I'm going to give you Pascal's triangle. 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Great. We're only going to use this line right here. Here we go. If I do the same argument for volume, I find that change in volume is approximately equal to, and you know, I'm dropping off some terms right here, but it's approximately equal to the 3 times alpha times the original volume times delta T, because of this pattern right here. You want to see that? I'll make you another video if you really want to see that spelled out. But there's this new definition. And some people like to say that delta V, the change in volume of something as it heats up, is, well, they would say equal, but maybe it's approximately equal to beta times V naught times delta T. And they want you to compare that to this other equation that says change in length, a linear expansion, is alpha times L naught times delta T. And you say, yep, those two equations are pretty similar, but all we need to do to connect these two, to connect the alpha and the beta, is to say that beta is 3 alpha. Yay!